In this lecture, we will discuss in more detail about the RC series AC circuit. So for that we have that same RC series AC circuit which consists of resistor having resistance R and capacitor having capacitance C. Both are connected with each other in series, and they are also connected with the applied alternating voltage source. Okay, so when the voltage is provided to the circuit, the electric field will develop inside this conductor, and that is result to the current, the alternating current in this circuit. Okay, so that alternating current will be constant when that pass through this resistor, and will have same value when that pass through this capacitor C, because we know that the current is same in all components of the series circuit. Okay, so only the change will be occur in the voltage. Okay, so here this voltage drop will be different from this voltage drop. Okay, so here if we add the voltage drop of this resistor and the voltage drop of this capacitor, okay, both will be equal to this resultant voltage. Okay, so here we have the phasor diagram for the power resistive circuit, and we know that in the power resistive circuit the current I and the voltage VR are in phase with each other. Okay, similarly we have the power capacitive circuit in which the current I will lead the voltage VC by 90 degree. So we have that scenario. Okay, so if we add these two phasor diagrams with each other, okay, it will give us the resultant voltage. Okay, so we are interesting to find this total this we have to add the voltage of this resistor and the voltage of this capacitor. Okay, and that will be equal to this resultant voltage. So we do not add that directly. Okay, so this is actually represented by this phasor diagram. Okay, so for that we will have to apply the rules of the vector algebra. In vector algebra, the addition is performed by the head to tail rule. First we will take this V of R, and I have taken this. Okay, so after that we will have to add this voltage VC, and that VC we will take from here and we will bring that to here. The tail of this vector VC, we will put that with the head of that first vector, and we will put that with the same magnitude here. From the head to tail rule, the resultant will be drawn from the tail of the first vector to the head of the last vector. So this is actually that resultant, and this resultant is actually the this applied voltage source. Okay, so because here we are interested to find this V, and we are going to add this VR and VC. So if we add this VR and VC, it will give us this V. So here we have the addition, the head to tail rule. By head to tail rule, we are going to add this VR and VC. It will give us this resultant, and so therefore we put V here. So this diagram is explained here in this circuit. We have that same RC series AC circuit. We have that applied voltage V and which is given by this vector, and here we will have vr, and which is given by this vector, and we will have vc, and which is given by this vector. So from here we see that there will be some phase difference between this resultant voltage and the voltage of the resistor and the voltage of the capacitor. So for that if we applied this voltage, the voltage will drop here, which is vr, and this voltage vr will be leading the provided voltage by angle phi. So this is actually this explanation is actually comes from this diagram. So here in this diagram we have this vr, and that is leading this resultant voltage v by this phi. So therefore I have draw the diagram for the graph for this v and vr, and here this vr is leading this v, and the remaining voltage will be passed through here, which is vc. And from this diagram we have, if we extend this rectangular component of this vector, and this is the other rectangular component of that this resultant vector. Okay, so this so from here this vc is lagging behind this v. Okay, so here this v is leading, and this vc is lagging behind that v. So therefore I have showed that graphically here that v is leading vc. Here this v is leading this vc, and after that the voltage v after that this will be the resultant voltage. Okay, so here we know that due to this voltage the current I will be developed inside this circuit, and that current I is the same because here the components are in series with each other. So we have that current I, the alternating current, and that will have this graph. Okay, and here this current I will lead this total voltage, this v. Okay, so that explanation is also given by this diagram. So here we have that current I, okay, which is common for both capacitor and resistor. So we have that current I. Okay, and this current I is leading this voltage v, okay, by angle phi. So we have that same scenario here. Okay, so first we are going to find the magnitude of this resultant voltage, then after that we will have to find this phi. Okay, so first I am going to find the resultant voltage. So for that we know that this side is the base. Okay, this is because this is adjacent with this phi, and this is the perpendicular, and this is the hypotenuse. So from the Pythagoras theorem, this hypotenuse square is equal to base square plus perpendicular square. So hypotenuse is actually this v, and this is equal to v square, and base is this vr. This is the base, v of r whole square plus perpendicular, which is this vc whole square. So we will have to put the value of this vr and this vc. So this vr is equal to ir, and which is equal to I r and whole square. So this VC is equal to IXC whole square. Okay, so from here we can write that V square is equal to I square r square plus I square xc whole square. So from this we will take the common I square. So that equation become this. So V square is equal to I square will be common, and that will become R square plus xc whole square. So we will take the square root on both sides. So this will become V, and here we will have that square root I square into R square plus xc square. Okay, so we have, this is the magnitude of this resultant voltage. Okay, so after this we will have to find the opposition upper to the flow of the charges inside this RC series circuit. Okay, so which is given by this. So for that we will have this V, and this is square root of I square. Okay, so this square root is on these two, and the remaining the square root of R square plus xc square. Okay, so this V is equal to I square, and square root will be cancelled, and here it will become I and into square root of R square plus xc whole square. So we can write this as square root of R square plus xc square, which is equal to V by I. Okay, so this is called the combined opposition upper by this resistor R and capacitor C in this circuit, and we call that combined opposition is impedance. So this is actually that impedance, and which is denoted by Z. So therefore we can write that above is Z is equal to V by I. So this is actually that opposition upper to the flow of the charges inside this RC circuit. Okay, so after that we will find this phi. Okay, that this phi is given by the tan theta. Okay, tan theta, and which is equal to perpendicular by base, and the value of the perpendicular is VC, and divided by base, and the base is VR, and we know from here VC is equal to IXC divided by IR. This I and I will be cancelled, and here it will become this. So tangent theta is equal to xc divided by r. Okay, so if we divide tan on both sides, okay, so this tan and that tan will be cancelled out, and here this will become this. So theta is equal to 1 over 10 into xc divided by r. Okay, so here this tan from here, this tan theta is so from here this tan theta, sorry, so from here the theta is theta or the phi. So these are actually the phi. Okay, so this phi is equal to tan inverse. So this, if it go to the denominator, it will become tan inverse into xc divided by r. This is the final equation for the phi. Okay, this is the final equation for the phi, and let's call this as a equation 3. Okay, so here first we determine this v. Okay, this is that the magnitude of this provided voltage, alternating voltage v. Okay, and here in this component, that provided alternating voltage v is lag behind the voltage of resistor. Okay, so how much, by which angle this is lag behind that? So for that we'll have to find the phi. So we find the expression for that phi, which is equal to tan inverse xc by r. So we know the value of xc, and we know the value of r, which is actually the resistance. The r is the resistance upper by that resistor. So if we know these two values, the phi, we will know that phi, and that phi is actually the degrees. Okay, so that phi is actually represent the degree by which this VR is leading this V. Okay, and similarly we have that same scenario. This V is lagging behind this VC, and that phase difference here, that the number of the degrees by which this V is leading this VC is given by this expression phi is equal to tan inverse xc by r. Okay, and similarly we have this voltage, and this is the current I, and here is also the angle. Okay, and that is given by this. Okay, so from here we conclude that here this voltage is leading by this phi, this voltage having magnitude this. Okay, having magnitude this is lagging from this VC by this phi, and here we have that same voltage having magnitude this. Okay, is lagging behind the current I, by this angle. Okay, so this is the expression for the RC series circuit. So if we know the value of resistance R and the value of the opposition of this capacitor XC, then we can easily find the resultant voltage and the angle by which that resultant voltage is leading or lagging. Okay, so now we have to discuss about the power. Okay, so we have this diagram for the power. Okay, this is actually the power for the RC series AC circuit. So for that we have this current I which is leading. So this yellow is actually the current I, and which is leading this voltage. This blue color is the voltage. Okay, so this voltage is lagging behind that yellow color current. Okay, and we have this scenario here. Okay, this current is leading and this voltage is lagging. Okay, so we have that same scenario and we draw that leading current and voltage in the same graph. Okay, so we know that power is equal to V, power is equal to V and I. Okay, so we will multiply this current I and this voltage V at each and every instant, and so that will give us the power at each and every instant. So here this red color shaded region is actually the power representation. Okay, and which is given by the multiplication of the current I and voltage V at each and every instant. Okay, so here the power is from this line will be, this reference point will be the above will be the positive and the lower will be the negative. So here we have this voltage V with this blue color. Okay, and this is the current I with this yellow color. So if we multiply their amplitude at each and every instant, so both are the positive. Okay, so therefore their power will be the positive. Okay, so here this power has increased because here the amplitude of these two has increased. So if we multiply that, the power will be increased. Okay, so similarly we have on this side we have the negative power. So why this negative? Because here in this position we have the current I which is the negative below this line, which is the negative. So if the current is the negative, and here in this region this voltage is the positive, so if we multiply this negative with this positive, it will give us the negative value. So therefore the resultant voltage is the negative. The resultant voltage is the negative in this region. Okay, so after this region this voltage become negative. Okay, here this is negative up to here, and we have that same current, this is also the negative. So if we multiply this negative with the negative, that will give us the positive. So negative multiply negative will give us the positive. So therefore the resultant voltage here is the positive. Okay, and at this region we have this current as a positive and this voltage is a negative. So if we multiply this positive with the negative, the resultant will be the negative. So therefore the voltage is the negative here. Okay, so for from here we conclude that the power here the value of this power is positive, the value of at this region the power is the negative, and here this again become the positive and this is become the negative. So if we see here in more detail, so this is actually that power which have larger value, which have large amplitude here. Okay, and on the negative side we have the less power. Okay, and again on the positive side we have the more power here. Okay, this shaded region is the more, and here this shaded region again the less. It means that here in the when the power is positive, the power will be delivered from the source to the RC circuit. Okay, so here this power is more delivered to that components of the RC circuit, and the less power is delivered by that component of the RC circuit towards the source. Again the more power is delivered by the source to the components of the RC circuit, and we have the less power delivered by the components of the RC circuit towards the source. Okay, so here if we add that, the more here the power will be it will give us the positive value, because these negative are very less. Okay, they do not cancel that positive sides, so the resultant of this power will be the positive. So if the power is the positive, so the power will be go from the power will be delivered by the source towards the RC circuit. In the other word, we can say that the power has consumed, that is comes from the source toward the RC circuit. So here the power consumption is more here in the RC circuit, and that power consumption is actually come from this resistor R, that is do not come from this capacitor, because capacitor do not consume the power is only consumed by the resistor. So this power consumption is attributed to only the resistor. Okay, so there is no power consumption by this capacitor C. Okay, so the average power in this case is so we have this other diagram here. This diagram we have that same, this is actually that same diagram. This diagram, if you see carefully here, we have this VR, VC and this V. Okay, we have that same diagram here, VR, VC and that V, and we have that phase angle phi. So we have three types of the power. One is the true power, and the other one is the reactive power, and the other one is the apparent power. So this power is actually the total power provided to the RC circuit. So when the total power is provided to the RC circuit, okay, the sum of the current will be dissipated inside that circuit. Here this due to in the form of electric field in the plate, between the plates of the capacitor, some of the power will be dissipated, and that power is called the reactive power. If we multiply this reactive power with this apparent power, it will give us this true power. Okay, so from here the power factor for the resistor is given. So I am going to give the topic here, the power. Okay, and we know that power is actually the multiplication of the current I and voltage V. Okay, so let's say first the power for the resistive circuit. Okay, in power resistive circuit, the power factor is 1. The power factor is equal to 1, because in the power resistive circuit the current I and voltage V are in phase with each other. So therefore cos 0 is equal to 1, and this cos phi is actually the power factor. Okay, and this power factor, this cos phi is actually given by this relation. So the power factor is equal to the true power, okay, divided by the apparent power. Okay, the true power divided by the apparent power. Okay, the true power divided by the apparent power. So here this true power is actually the base, and this is actually the hypotenuse. So if we divide the base by hypotenuse, it will be equal to cos phi. So here we have that phi, so it will be equal to cos phi. So therefore we have written here this cos phi for the power factor. So here this power factor is equal to cos phi, and here in the pure resistive circuit, the current I and voltage V are in phase, so therefore the power factor for that is 1. And also we have the power for pure capacitive circuit. We know capacitive circuit is actually the circuit which consists of the alternating source and the capacitor C. So in that case the current will lead the voltage by 90. So therefore we know that power factor in that case is equal to cos phi, and here phi is the angle between the current I and voltage V, and in the case of the capacitor that angle is 90. So therefore cos 90 is equal to 0. So the power factor is 0 in case of the pure capacitive circuit. So if we take the average of these two, if we take the if we take the average, so here we will have the power, okay, which is given by IV, okay, and here the power will be 0. So the average power from here, the average AVG, the average power is equal to this power, which is equal to 0 and plus IV cos phi. So therefore it is equal to IV cos of phi. This is the average power in this case. So this is actually that average power here, okay, which is actually the multiplication of the current I and voltage V. Okay, so this was all about from my side, okay, and this is the end of the explanation of the RC series AC circuit, and that's it guys. Thanks for watching.